Beneath its famous dolce vita art and opera lies Italy's turbulent geology. Let's explore the Apennines, the backbone of Italy, along with recent tectonic events. We will examine its famous volcanoes, along with the impact that tectonics have played throughout the history of Italy. Italy's rich culture of art, history, and cuisine is often what comes to mind, but beneath its picturesque surface lies a complex and dynamic geological story. This presentation will delve into the powerful tectonic forces that have shaped the Italian peninsula, from the formation of the Apennine Mountains to the country's active volcanoes, and the seismic events that continue to impact its landscape and history. A map illustrating Italian seismicity from 1900 onward shows a dense concentration of earthquakes primarily tracing the spine of the Apennine Mountains, extending from the north down to the southern regions of Calabria and Sicily. This pattern reflects Italy's position at the complex boundary of the African and Eurasian tectonic plates, making the country prone to significant and frequent seismic activity. The clustering of epicenters in these regions highlights the main seismic hazard zones on the peninsula. When we think of Italy, we picture ancient Rome, incredible art, and delicious food. But underneath all of that, the country is actually a geological hotspot, constantly on the move. The most important part of this story is the Apennine Mountains. These aren't just scenic hills, they're the spine of Italy, and they've been pushed up over millions of years by the colossal force of two continents colliding. Imagine the African continent slowly but relentlessly pushing up against Europe. That's what's creating these mountains. Historically, Italy has suffered some of Europe's most catastrophic quakes. The 1908 Messina earthquake picture here and ensuing tsunami remain the deadliest, claiming up to 120,000 lives. More recently, the 2009 L'Aquila earthquake highlighted ongoing vulnerabilities in central Italy, as discussed later. These seismic events underscore the powerful, destructive forces that have repeatedly shaped Italy's history and continue to influence its landscape and building practices today. The 1908 Messina earthquake was the most destructive seismic event in European history, striking the Strait of Messina between Sicily and Calabria on December 28th. The magnitude 7.1 to 7.5 earthquake and the subsequent tsunami virtually destroyed the cities of Messina and Reggio Calabria. An estimated 75,000 to 120,000 people perished, primarily due to the collapse of poorly constructed stone buildings while residents were sleeping. The catastrophic scale of the disaster prompted the Italian government to establish the first comprehensive seismic building codes for the region. Italy's turbulent geology is a continuous force, with seismic activity remaining a frequent reality for the country. This diagram provides a clear visual record of this ongoing dynamism, plotting the numerous earthquakes that have occurred across the Italian peninsula over the last 2 decades. The map shows the most significant Italian earthquakes in the last 20 years. The Emilia-Romagna earthquake struck on Sunday, May 20th, 2012. The magnitude 6.0 tremor struck at 4:04 a.m. with its epicenter about 35 kilometers, 22 miles, north of Bologna at a relatively shallow depth of 5 kilometers, 3.2 miles. The August 2016 Amatrice earthquake was a devastating event that occurred in a highly seismic region of the central Apennines. The shallow magnitude 6.2 quake struck at night, causing the collapse of countless old masonry buildings and resulting in the deaths of 299 people, mostly in the heavily damaged towns of Amatrice, Accumoli, and Arquata del Tronto. Here is an image of the destruction caused by the Amatrice magnitude 6.2 earthquake. The earthquakes that struck Viso in October 2016 were part of a powerful series of aftershocks following the devastating Amatrice earthquake 2 months earlier. The largest of these, a magnitude 6.1 quake on October 26, caused widespread damage to already weakened buildings, but fortunately its timing allowed many people to be safely out of their homes, resulting in a low casualty count. 86 kilometers east of Naples, the 1980 Irpinia earthquake was a major seismic event that struck southern Italy on November 23, 1980, with a magnitude of 6.9. The quake and its aftershocks devastated a large area, leaving at least 2,483 people dead, over 7,700 injured, and 250,000 homeless. It became a powerful and tragic symbol of Italy's vulnerability to seismic activity and led to significant changes in the country's civil protection and disaster response protocols. What are the plate tectonic forces causing earthquakes and volcanism? The Earth's crust is a restless puzzle of massive plates that are constantly in motion, a force that silently shapes our world. This dynamic interaction between plates is the primary cause of earthquakes and volcanism, creating both the dramatic landscapes and the natural disasters that define our planet's geology. Earth is cooling off, and energy is trapped in the interior of the planet. The internal heat of the Earth is the ultimate source of energy that drives plate tectonics, which in turn causes earthquakes and volcanism. This heat creates convection currents in the mantle that cause the tectonic plates to move and interact with one another. When these plates collide, separate, or slide past each other, the immense energy of their motion is released as earthquakes and volcanic eruptions. Pictured here are the three main types of tectonic plate movement. Subduction. When two tectonic plates collide and one is pushed underneath the other, this process is called subduction. This usually happens when a denser oceanic plate meets a less dense continental plate. The oceanic plate sinks into the Earth's mantle where it melts, often leading to the formation of volcanoes and deep ocean trenches. Mid-oceanic rifting. This is when two plates are pulling apart from each other. As they separate, molten rock from the mantle rises up to fill the gap, creating new oceanic crust. This process, also known as seafloor spreading, forms long underwater mountain ranges called mid-ocean ridges. The Mid-Atlantic Ridge, where the North American and Eurasian plates are spreading apart, is a classic example. Transform fault motion. This type of motion occurs when two plates slide horizontally past each other in opposite directions. The plates do not move smoothly, but rather grind against one another, building up immense stress. When this stress is suddenly released, it causes powerful earthquakes. The San Andreas Fault in California is the most famous example of a transform fault. The subduction of the Adriatic plate beneath the Eurasian plate is indeed the primary driver for the formation of the Apennine Mountains. However, the volcanism in Italy is caused by a more complex and debated process. The volcanoes of central Italy, such as Mount Vesuvius, are a result of the subduction of the Adriatic plate, As this plate sinks, it undergoes a process called back arc extension on the other side, which can create conditions for magma to rise to the surface. An Oreo cookie, with its top part cut in half and pressed under the other side, is a great way of understanding subduction. On the other hand, if you break the top of the Oreo cookie and pull it apart, that is what is happening at the mid-ocean ridges, where new magma is being created. And finally, cracking the top of the cookie and sliding them past each other explains the motion along plate boundaries that are moving laterally. Putting it simply, an earthquake is a sudden break of rock formations in response to the buildup of stress along active plate margins. Earthquakes are measured using the Richter scale. An earthquake's ranking on the Richter scale is a measure of the size and magnitude of an earthquake. It was developed in 1935 by Charles F. Richter to compare the strength of different earthquakes. A magnitude 6 earthquake is 100 times greater in seismic wave amplitude and releases about 1,000 times more energy than a magnitude 4 earthquake. The Richter scale is logarithmic, meaning each whole number increase represents a 10-fold increase in wave amplitude and a 32-fold increase in energy. This is why a small numerical difference on the scale translates to a massive difference in an earthquake's power. The Mediterranean region is one of the more complex geological areas on Earth and appears as a junction of many plate boundaries and a hodgepodge of several ill-defined small plates between the two large plates of Eurasia and Africa. The main plates to consider when discussing the tectonics of Italy are the Adriatic plate and the African plate. The primary earthquake zones in Europe and the Mediterranean are a result of the African plate colliding with the Eurasian plate. This collision creates intense seismic activity throughout the Mediterranean basin, particularly in the Hellenic Arc around Greece and along the many active faults in Italy. Turkey is also a high-risk area situated on the Anatolian microplate, which is squeezed westward by the Arabian plate, causing frequent, powerful earthquakes along the North Anatolian fault. These regions are the main areas of tectonic stress and seismic events in the European area. Let's go back 175 million years when Pangaea, the youngest megaplate, started to break up. At about 190 million years ago, during the early Jurassic period, the supercontinent Pangaea was still largely intact. The immense single landmass was C-shaped, with the bulk of its mass stretching from the northern to the southern poles. Large curving embayment known as the Tethys Sea is on its eastern side. The following animation shows the various stages of the breakup of Pangaea to the final closure forming the Mediterranean Sea. Looking at the map, the Tethys Sea was compressed into the current Mediterranean Sea, Black Sea, and Caspian Sea. The Rock of Gibraltar is a Jurassic limestone promontory that was uplifted from the seabed by the immense pressure of the African tectonic plate, pushing northward into the Eurasian plate. This ongoing collision over millions of years folded and faulted the rock layers, raising them to their current dramatic position. This diagram shows the numerous volcanic activities of the past and present in Italy. We will discuss the three active volcanoes, Mount Vesuvius, Mount Etna, and Stromboli. The diagram is showing the compressional forces folding and faulting along the Apennine mountain chain as a result of the compressional forces of the Adriatic plate and the subduction of the Adriatic plate under the spine of Italy. This is a sandbox simulation of the type of stresses that caused the folding and thrusting along the Italian Apennine mountain chain with the Adriatic plate compressing the rocks on the eastern side of Italy. Apennine Mountains near Carrara, Italy. This area is a good example of mountain uplift and folding. The Carrara marble quarries in Italy have been in continuous operation since Roman times, when the stone was called marmor lunense and used to construct monumental buildings like the Pantheon. Production slowed after the Roman Empire's fall, but experienced a major revival during the Renaissance, becoming the favored material of sculptors like Michelangelo, who personally visited the quarries to select blocks for masterpieces like David. Today, the Apennine Alps outside Carrara contain hundreds of quarry sites and remain one of the most prolific marble extraction districts in the world. Marble is a metamorphic rock that starts as limestone and is transformed by the Earth's heat and tectonic pressure, which causes the original rock's tiny grains to fuse into a strong, beautiful mass of interlocking crystals. This is an image of the Basilica of Santa Croce, Florence, with its extensive Carrara marble facade, and the Duomo di Siena, Siena Cathedral. Carrara marble is most famous for its use in some of the world's greatest classical architecture due to its brilliant white color and fine grain. Ancient Roman landmarks like the Pantheon and Trajan's Column were constructed with Carrara marble, as well as the Marble Arch in London, and surprisingly enough, also much of the exterior of the United States Capitol building in Washington, D.C. This is a picture of the Cathedral of Saint Mary of the Flower il Duomo di Firenze with its Carrara marble facade. Carrara marble is most famous for its use in some of the world's greatest sculptures, such as Michelangelo's David in Florence, Italy, and Michelangelo's Pietà, St. Peter's Basilica in Vatican City. Let's discuss Mount Vesuvius, the massive active volcano in Naples. Naples is a city of 2 million people that flourishes beneath Vesuvius's great ashen shadow and the Phlegraean fields. The photograph shows a reconstruction of Vesuvius before its great eruption in 79 AD. The area encompassing Mount Vesuvius is typically measured by the size of the Vesuvius National Park, which was established to protect the volcano and its surrounding ecosystem. The area of the Vesuvius National Park is approximately 28 square miles. The volcano itself, known as the Summa Vesuvius Volcanic Complex, is a major feature within this protected area. This is what the eruption of Mount Vesuvius may have looked like. Plinian volcanoes are named after Pliny the Elder, a great historian who died in the Vesuvius eruption. The Vesuvius eruption of 79 AD released a catastrophic volume of volcanic material estimated to be between 3 and 4 cubic kilometers of dense rock equivalent magma. This material, ejected at a rate of 1.5 million tons per second, formed an eruption column up to 33 kilometers high. The resulting fallout buried the surrounding settlements under thick layers of debris. Pompeii was covered by about 2.8 meters, 9 feet, of ash and pumice, while Herculaneum was overwhelmed by pyroclastic flows up to 20 meters, 65 feet deep. Vulcan, Latin Volcanus, was the Roman god of fire, the forge, and metalworking. The term volcano is named after him. Vulcan presided over both the beneficial aspects of fire, like the smith's forge and the warmth of a hearth, and its destructive aspects, like volcanoes and wildfires. He was the patron deity of blacksmiths, artisans, and all craftsmen who worked with metal. The famous Joseph Turner painting of the eruption of Vesuvius is shown. The artistic concept emphasized the awe, terror, and wonder that humans feel when confronted with the terrifying, overwhelming, and infinite power of nature. A colossal volcanic eruption perfectly embodied this idea of majestic destruction. Vesuvius ejected a cloud of stones, ash, and fumes to a height of 33 kilometers, 20.5 miles, spewing molten rock and pulverized pumice at the rate of 1.5 million tons per second. It was 100,000 times the power of Hiroshima bombing. An estimated 16,000 people died due to hydrothermal pyroclastic flows. It buried Pompeii and Herculaneum. The only surviving eyewitness account of the event consists of 2 letters by Pliny the Younger to the historian Tacitus. In 1863, archaeologist Giuseppe Fiorelli developed a technique. He and his team carefully poured liquid plaster of Paris into these cavities of the dead. Once the plaster hardened, the surrounding ash was removed, revealing a detailed 3-dimensional cast that perfectly immortalizes the person's final pose and even their facial expressions. If you visit Pompeii, you can easily view Vesuvius about 6 miles to the north. In 1944, Vesuvius erupted during World War II. The tephra and hot ash damaged the fabric control surfaces, engines, plexiglass windshields, and the gun turrets of the B-25 bombers. Estimates ranged from 78 to 88 aircraft were destroyed. The U.S. Army Air Force's 345th Bombardment Group was based at Pompeii Airfield near Terzigno, Italy, a few miles from the eastern base of the mountain. Herculaneum was only 5 miles from the Vesuvius crater. The key difference in the burial of Pompeii and Herculaneum relates to the type and velocity of the volcanic material they received. Pompeii was buried by several feet of ash and pumice fall, with a layer of about 16 to 20 feet deep. Herculaneum, situated closer and to the west, was later engulfed by multiple fast-moving and extremely hot pyroclastic surges and flows, resulting in a much deeper deposit of solidified, carbonizing material that reached up to 65 to 82 feet deep. The famous ship sheds, or fornici, in Herculaneum are located there because the town was a seaside settlement with a busy port on the Bay of Naples. These vaulted structures were originally used to store and shelter boats right along the ancient beach and shoreline. The discovery of over 300 skeletons huddled within these sheds confirms this was the spot where residents fled, hoping to escape the eruption by sea. The Amalfi Coast also received up to 2 meters, such as seen in Positano from the AD 79 Vesuvius eruption. The prevailing winds pushed the volcanic fallout to the south-southeast, directly blanketing the Sorrento Peninsula and the Amalfi Coast. The Phlegraean fields west of Vesuvius are a series of ancient but active caldera. Phlegraean means burning fields. The Phlegraean fields, Campi Phlegrae, are a massive and highly active volcanic caldera located just west of Naples, Italy, and about 15 miles from Mount Vesuvius. Unlike Vesuvius, which is a single cone-shaped stratovolcano, the Phlegraean fields are a vast sunken depression formed by the collapse of the ground following two massive prehistoric eruptions. It's a complex system that includes about 24 craters and volcanic edifices, many of which are underwater in the Gulf of Pozzuoli. Bradycism is the slow, periodic rising and falling of the Earth's surface, often seen in volcanic regions like Italy's Campi Phlegrae. It's essentially the ground breathing caused by changes in pressure from the buildup or release of magma or hot underground fluids, hydrothermal activity. This slow movement, which gets its name from the Greek words for slow and movement, can be dramatic. It's what has historically caused coastal areas to gradually sink underwater and then reappear. The process is often characterized by a period of uplift followed by small earthquake swarms. Campi Phlegrae last eruption was in 1538, which formed the new cone of Monte Nuovo, and the area is constantly monitored due to its proximity to the densely populated city of Naples. The dramatic ground movement has resulted in over 3 meters of vertical uplift in recent decades. It is fundamentally governed by an internal cement seal. This seal is a caprock layer composed of pozzolanic ash and volcanic rock. The seal acts as a pressure trap. When gases and fluids rise, the caprock contains the pressure, forcing the ground to inflate or breathe up significantly. However, when the stress exceeds the rock's limit, the seal fractures, hydrofracturing, causing bursts of earthquakes and subsequent ground subsidence. The engineer and writer Vitruvius documented this, noting that this astonishing powder was the key to building piers and harbors that were impregnable to the waves, as Pliny the Elder later boasted. This discovery was critical because it allowed them to build structures like the Pantheon's massive dome and create waterproof harbors, feats of engineering that relied entirely on a chemical reaction that happened naturally in the caldera's rock and that they simply perfected for their own use. The mollusk holes visible on the columns of the Macellum of Pozzuoli marketplace are considered the most compelling and famous evidence of bradycism, the slow vertical movement of the Earth's surface in the Campi Phlegrae volcanic area. These specific holes, bored by saltwater mollusks known as date mussels, only occur when the rock is submerged in the sea. Since the Roman market building was originally constructed on dry land, the presence of these boreholes, which span the columns up to several meters above the current floor level, proves that the entire site sank below sea level long enough for the mollusks to colonize the stone. The vertical band of holes serves as a geological tide gauge, demonstrating that the area underwent a prolonged period of subsidence, sinking, followed by a subsequent period of uplift rising. Pillars rose and sunk after they were built. The mollusk bore holes on the pillars were created during their time of submergence. And the pillars have not tilted. This gradual, non-catastrophic movement convinced 19th century geologists like Charles Lyell that the Earth's crust could change slowly over long periods of time. Charles Lyell used the marketplace of Pozzuoli as the cover for the first book written on the science of geology. Without the Roman discovery of concrete, the enormous engineering and architectural feats of the Roman Empire would not have been possible. This concrete discovery easily distinguished the Greek architecture from the Roman. Romans developed the pozzolanic ash to bind with lime to create concrete for buildings and underwater construction. Pictured here is the Great Colosseum of Rome. The Zaguan Aqueduct is an impressive ancient Roman aqueduct that supplied water to the city of Carthage, Tunisia, from springs near the town of Zaguan. At approximately 132 kilometers long, it is counted among the longest aqueducts built in the Roman Empire and remains a testament to ancient Roman engineering. The Caesarea Maritima Aqueduct in Israel is a magnificent Roman structure, originally commissioned by Herod the Great to supply fresh water to his newly built port city from springs near Mount Carmel. It is particularly striking as a well-preserved dual-channel high-level aqueduct with sections of its arches dramatically visible along the Mediterranean coastline. The 7 hills of Rome were primarily formed from a large volcanic plateau. This formed massive layers of tuff, a type of rock made from compacted volcanic ash and debris. Over time, the Tiber River and its tributaries, along with natural erosion, carved out the valleys between these layers, isolating them to form the distinct hills. The diagram shows the older river channels in blue that created the 7 hills of Rome. Pictured here is the Capitoline Hill in Rome and the example volcanic tuff exposed at the base of the hill. The primary volcanic systems near Rome are the Alban Hills, Colli Albani to the southeast, and the Sabatini Volcanic Complex to the northwest, both of which are currently considered dormant. These are not cone-shaped mountains, but large caldera complexes, with their craters now partially filled by scenic lakes like Lake Albano and Lake Bracciano. Lake Albano volcano near Rome, thought to be extinct, is waking up. Steam vents and water rising 2 millimeters per year are being monitored. The Alban Hills volcano, in particular, exhibits ongoing signs of unrest, including ground uplift and minor seismic activity. Let's discuss Mount Etna to the south in Sicily next. The collision between the African plate and the Eurasian plate creates a complex geological setting beneath Sicily, where the African slab is slowly subducting or plunging beneath the Eurasian plate. This intense tectonic compression is responsible for the formation of the island's mountain ranges, frequent earthquakes, and the presence of active volcanoes like Mount Etna and the Aeolian Islands. Here is a picture of Mount Etna from the International Space Station, October 30th, 2002. The dark plume rising from the top of the volcano is an ash cloud. The white are forest fires. According to Greek and Roman legend, the Strait of Messina was treacherous. The Strait of Messina is a narrow 32-kilometer-long channel separating the island of Sicily from the Italian mainland, Calabria, and it connects the Tyrrhenian Sea to the Ionian Sea. This bottleneck is famous for its exceptionally strong tidal currents, eddies, and whirlpools, which were historically associated with the Greek myth of the sea monsters Scylla and Charybdis. While the Greek hero Odysseus narrowly escaped the strait's powerful whirlpool, Charybdis, and the rock-dwelling monster Scylla during his post-Trojan War voyage, the Trojan hero Aeneas successfully steered clear of those same dangers by following a prophetic warning to avoid the channel and sail around Sicily instead. The Strait of Messina features a shallow underwater ridge, sill, in its center, flanked by deep basins in the Ionian and Tyrrhenian seas. This choke point forces strong alternating tidal currents to flow across it, which in turn generates intense turbulence, whirlpools, and internal waves as different water masses mix. Water levels are always different between the north and south of Sicily. That creates a considerable flow through the passage, regardless of weather conditions. The ancient Greeks and Romans feared the monsters Scylla and Charybdis because they were the physical embodiment of a deadly navigational hazard in the Strait of Messina. The Scylla was a terrifying creature, originally a beautiful nymph transformed by magic with a dog-like lower body, who lived in a cave and would snatch sailors from passing ships with her 6 long necks and heads. Charybdis, on the other side of the narrow strait, was a massive whirlpool that would suck down the ocean water 3 times a day, only to violently spew it out later, instantly destroying any ship caught in her powerful maw. The choice sailors faced was a perilous one: sail close to Scylla and lose some men, or steer toward Charybdis and risk losing the entire ship and crew. Lastly, let's discuss the Aeolian Islands and the Stromboli volcano. The Aeolian Islands archipelago, off the coast of Sicily, is a chain of 7 volcanoes formed by the subduction of the African plate beneath the Eurasian plate. While most of the islands are dormant or extinct, Stromboli is one of the most consistently active volcanoes in the world. Its nearly continuous mild Strombolian eruptions, which typically occur every 10 to 20 minutes, involve moderate explosions that launch incandescent fragments of lava, ash, and lapilli hundreds of feet into the air. Mount Stromboli has had almost continuous eruption for the past 2,000 years. Strombolicchio, meaning Little Stromboli, is a small towering sea stack located about a mile northeast of the main island of Stromboli. Geologically, it is a volcanic plug of extremely hard, erosion-resistant basalt, representing the eroded remnant of the original volcano that was active approximately 200,000 years ago, before the current Stromboli cone began to form. Thank you for watching, and we hope you enjoyed this presentation. Please subscribe to our YouTube channel by pressing the subscribe and like buttons below. We are planning to add many more presentations covering a wide variety of science, history, and other enriching subjects. If you have any comments, questions, or suggestions, please feel free to make them, and we will do our best to respond. Again, thanks for watching, and please do subscribe.